Hello, my name is Brandon, and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome. If you're a returning viewer, it is great to have you back. If you like the video, please give it a thumbs up and share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. So now that we know each other, let's go ahead and get started. So this video is the next in my series on basic inferential statistics. More specifically, sample proportions. So in many previous videos, we talked about sample means. So we go out and collect some continuous data and we find the sample mean. We can do lots of things with that. So sample proportions are similar, but it's a different kind of data. And actually underneath, it's very simple. But when we talk about other things like the standard error of the sampling distribution and finding probability intervals, it can get a little bit more complex. But almost everything you're going to see here goes back to what you saw talking about sample means. So we're going to go from sample means to sample proportions with a few similarities and a few differences. So let's go ahead and get going. So this video is brought to you by the great people at the Great Courses Plus. Chances are, if you're watching this video in the first place, it's because you need to or want to learn something. And there are few better places to learn about anything than the Great Courses Plus. They have over 11,000 video lectures on almost any topic imaginable, from photography to philosophy to history, literature, to gardening, and yes, of course, math and statistics. And luckily, the Great Courses Plus are giving my viewers a free trial. So please click on the link in the description below to support this channel and of course support the Great Courses Plus. So let's go ahead and get started on our topic. So what's going on at the Moonlight Cafe? The administration at Caffeine State University, or CSU, is considering the addition of a late-night cafe to the student union called Moonlight Cafe. It will have drinks, snacks, comfortable furniture, and plenty of study space. To learn more about student interest, the administration hires a grad student to go out on campus and survey 30 students. Yes or no? Would you study at Moonlight Cafe at least once per week? The result of the survey is that 17 out of 30 students answer yes. So the result is called a sample proportion. Now mathematically, this is a very simple concept. So the sample proportion is represented by P bar. So remember, the sample mean is X bar, the sample proportion is P bar. And that equals X over N, where X is the count of the observations in the sample that have what you are interested in. So in this case, it's who answers yes. N is the number of observations in the sample, which again in this case is 30. So quite simply, we have P bar equals X over N, which equals 17 over 30. It's just a simple fraction. That is 0.567 as a decimal, or 56.7% as a percentage. So very simple and very straightforward. So the sample proportion P bar is similar to a sample mean, which was X bar. It is just one of numerous samples that could be taken from the overall population. So in this case, the population is the entire student body of Caffeine State University. Now, if someone else went out and did the survey again, it's likely there would be a different result, just like we did for sample means. However, sample proportions are different than sample means in important ways. So a sample proportion represents what is essentially a nominal, so usually a binary variable. So something like yes, no, true, false, agree, disagree, and like elections could be Democrat, Republican, etc. So usually it's binary, meaning two options, and they are exclusive. So you can't be yes and a no or something like that. So it is a count or frequency of a nominal variable of interest. Now I will say at this point, there are proportions that have more than two options, and you can compare those proportions, and we'll get to that eventually. But for the sake of this video, we're going to stick to two options, a binary choice of yes, no, true, false, etc. So in that sense, it is related to the binomial distribution. I don't want to get into the weeds here, But if you remember, there's a specific distribution called the binomial distribution where we talk about successes and failures where we have two options. So the sample proportion is somewhat related to that, and you might see some similarities as we go forward. For the sake of just learning this concept, it's not overly important, but I just wanted to point out that it is similar to the binomial. So what is the expected value of p bar, the sample proportion? So the expected value equals p, which is the population proportion. So the expected value of the sample proportion, p bar, the mean of all potential values of p bar, is equal to the population proportion, p. So another way of saying that is that if we went out and took many sample proportions from the same population over and over and over and over again, the mean of all those sample proportions is the population proportion, or the expected value of p, which is E of p bar. So the way to think about this is that the expected value of the population proportion is just taking many, many samples and finding the mean of all those sample proportions. That's the expected value. So if we went out and took many sample proportions over and over and over again, and we collected all those sample proportions, we put those into its own distribution. So what we'd have is a sampling distribution. If you remember from the previous videos, we talked about the sampling distribution for the mean. Now, any distribution like that is going to have its own standard deviation, and the name of that is called the standard error. So the standard error is the standard deviation of a sampling distribution, and that goes for sample means or sample proportions. So we refer to the standard deviation of the sample proportion as the standard error of the sample proportion. However, the standard error of p bar, our sample proportion, is dependent on a question, and this is unique to sampling proportions, not sample means. Is the population of interest finite or infinite? So what we're really asking is the sample size large or small in relation to the population? For example, are we taking a sample of 15 from a population of 20 students, like maybe just one classroom, or 200 students, like a very large lecture, or 15 from 2,000 students, maybe a small college? So we're looking for the relationship between our sample size and the overall population that we're interested in, and we have to ask this question. Now note that in almost all cases in practice, like in your class or whatever else, we are assuming the population is infinite or very large or large enough in relation to the sample size. So this is probably not something you're going to have to worry about doing your homework or something else like that, because we kind of assume that the sample size is small relative to the overall population, but we just have to ask ourselves that question, or at least note if it's out of the ordinary because we're taking it from a very small population. So depending on the answer to that question, we have a slightly different standard error. So the standard error is sigma sub p bar. And again, remember for sample means, it's sigma sub x bar. Same notation, very similar. So on the left, we have the standard error if we're taking it from a finite population. And on the right, we have the standard error if we're taking it on a infinite population. They're very similar except for the one expression there at the beginning. So that is called the population correction factor. We only employ that if we're taking a sample from a population that's small relative to our sample. So the general rule is that if small n, the sample size, over big N, the population size, is less than or equal to 0.05, we use the infinite population. Now, if small n over large N is greater than 0.05, we have to use that correction factor. So again, in practice, this is probably something you'll never have to encounter, but if you are doing small samples and small population work, then you'll have to keep this in mind. So for example, we're sampling 30 students on a large college campus. So we're definitely going to use the infinite population standard error over here on the right. So if our sampling distribution of sample proportions is approximately normal, we can go ahead and find z-values like we did in sample means. So we do that the exact same way. To find a z-value, we take the sample proportion, in this case, P bar, minus P, which is the population proportion, divided by the standard error. And when we extract everything out and substitute, we have the expression over here on the right. So this is the same basic form as the sample mean. So remember, to find a z-value, we took x bar, which is the sample mean, minus mu, which is the population mean, divided by the standard error, which in that case was sigma divided by the square root of n. So if you look at these two, they're very similar. So we have the difference between the sample and the population divided by the standard error in each case, so the same basic form. So now it's time to P bar. So here's our sample proportion. So remember that was 17 divided by 30, or 0.567. So now we can calculate the standard error using our formula down here. We substitute everything in. So for P, we have 0.567, and then 1 minus that. We multiply those together, divide by n, which is 30, and then take the square root of all that, and we have 0.0905. So the standard error of P bar, our sample proportion, is 0.0905. So before we go any further, we have to run two tests. And again, in normal, class or homework problems you're having, you probably won't have to do this. You might, but I'm just going to mention it because I would be derelict if I did not. So we have to make sure that we can use the normal distribution for our sampling distribution in this case. And it's very simple to do. We got to run two quick tests. So the first is n times p greater than or equal to 5. We're evaluating this as true or false. So we do that math out. We end up with 17.01. That is greater than or equal to 5, so that is true. And then we do the other side. So we do that math, and we end up with 12.99. That is greater than or equal to 5. That is also true. So as long as those are both true, we can use the normal distribution as an approximation of our sampling distribution for the sample proportion. And here it is. So once we pass the two tests in the previous slide, we can go ahead and use this normal distribution to represent our sampling distribution for the sample proportion. So our sample proportion was 0.567. So we take that and we center that in our sampling distribution right here in the middle. Remember, that is a z-value of 0 right here in the middle. Our standard error is 0.0905. And what that represents is a z-value of 1. So we can go ahead and put 0.0905 above 1, a z-value of 1, and then the negative of that is a z-value of -1. So think and remember that a z-value of 1 is just another way of measuring the standard error, which is 0.0905. It's like measuring something in centimeters or inches. The distance on paper is the same. You're just measuring it with a different unit. So they're the same distance, just different units. So we go ahead and do the addition and subtraction, and now we can place actual values for each z-value. So if you look here at the z-value of 1, we take 0.567 plus 0.0905, and we end up with 0.6572. Then we do that again and again to get a z-value of 2 and a z-value of 3. Then we do the other half of the distribution by subtraction. So 0.567 minus 0.0905, we get 0.4762, and then -2 and -3. So now we have the actual values for our z-values. So if you remember something called the empirical rule, and that says that about 68% of our sample values should be within one standard error, or a z-score of 1 from the mean. So if we did this over and over and over again, we would expect about 68% of those values to fall in this interval. Now, about 95% within 2 standard errors, or a z-value of ±2. And about 99%, or almost all values, should fall between plus or minus a z-value of 3 or 3 standard errors. in each direction. So what about a probability interval using that sampling distribution? So the administration would like to know the probability of obtaining a sample proportion that is between 0.55 and 0.65. So we're interested in a sliver of that sampling distribution. So we can use the sampling distribution to find this probability just like we did for sample means. Exact same process. So here's what we're looking for. We're looking for the probability of obtaining a sample proportion that is between 0.55 and 0.65. So we're looking for a sliver of that distribution. So what we're going to do is find two probabilities and then subtract one from the other. So the first thing we're going to do is find the cumulative probability of having a sample proportion of 0.65. Then we're going to find the probability, the cumulative probability that is, of a sample proportion of 0.55. And then what we're going to do is subtract the smaller one from the larger one, and we'll end up with the difference. And that will give us the sliver in the sampling distribution that we are interested in. So visually it looks like this. So here's the upper value we're interested in, so 0.65. Here's the lower value we're interested in, 0.55. And you can see how those fall relative to the values along our bottom axis. And we're interested in the difference. So we're going to take everything from the left to the upper value, everything from the left to the lower value, subtract, and then we're going to get this gray sliver in the middle, which is what we want right there. We're looking for the area of that section. So the first thing we have to do is find the z-value for that upper boundary. And we do that very simply by subtracting the upper boundary, 0.65, minus the sample proportion, which is 0.567, divided by the standard error. So what we're asking here is how many standard errors, how many standard deviations, is 0.65 above the mean. So in this case, we do the math and we have 0.9171. So the sample proportion of 0.65 is 0.9171 standard errors, or a z-value of 0.9171. Same thing with the lower. So 0.55 minus the sample proportion divided by the standard error, and we end up with negative 0.1878. So the sample proportion of 0.55 is, you can say it either way, so 0.1878 standard errors below the sample proportion. So again, we just subtract. So we find the probabilities, the cumulative probabilities, using our z-score table in the back of the book or online, phone app, whatever you have. So the cumulative probability to a z-value of 0.9171, remember that's the longest one that we had in the previous slide, is 0.82. So that represents 82% of the area under that curve. Then we find the cumulative probability, left to right, of 0.55, a sample proportion of 0.55. That is 0.426. So that's 42.6% of the area under the curve. Then we just subtract out the smaller one, and we end up with what we want. So we go ahead and do that, and that is 0.394. So approximately 39.4% of sample proportions are between 0.55 and 0.65 if we collected many, many samples over and over and over again. It looks like this. So here was our upper boundary. Here was our lower boundary. And that's what we got. So we can expect about 40% of sample proportions to be in this interval. So quick review. First, we found the sample proportion. Then using the sample proportion and the sample size, we calculated the standard error of the proportion. The standard error of the proportion is the standard deviation of the sampling distribution, in this case of sample proportions. Next, we checked to make sure we could use the normal approximation for the sampling distribution. Remember, that was the two true tests we did on that one slide. If yes, we can go ahead and use the standard error to find z-scores or z-values. So using z-score cumulative probabilities, we were able to find probability intervals. Now, I want to note here that you've heard the word interval before. So what we're doing here is not a confidence interval per se. We'll get to that. So all we're doing here is finding slices of the sampling distribution. Okay, and we could do that for any two values. So confidence intervals we'll get to later. This video is brought to you by The Great Courses Plus, where you can get unlimited access to over 11,000 video lectures taught by award-winning professors from the Ivy League and other top schools around the world. You can learn about anything that interests you: science, literature, photography, gardening, and yes, statistics, like this lecture from Professor Tim Chartier called "Got Data? What Are You Wondering About?" from his course, Big Data: How Data Analytics is Transforming the World. And right now, The Great Courses Plus is offering my viewers a free trial and is also now optimized for Australia and the UK. So go to thegreatcoursesplus.com/Brandon Foltz, my name, to have access to the over 11,000 video lecture library, or click on the link in the description below. Okay, so that wraps up this video on an introduction to sample proportions. Again, many of the things we saw in this is very similar to sample means. Okay, it's a different kind of data, but when we found the standard error and everything, the forms of those were similar. When we found the z-values in the sampling distribution, that was all the same. So there are a lot of things you can carry over from sample means to sample proportions. So anyway, I hope you liked the video. Again, if you like it, please give it a thumbs up. Share it with anyone you think might benefit from watching. And thank you for your time, and I look forward to seeing you again in our next video. Goodbye.